Okay, so good morning, everyone. I'm Raphael. I'm going to introduce Mia, and then we will have her lecture, which will be about 45 minutes, right? And then we hope we'll have a good amount of time for questions, and we'll let everyone run away to do their regular Sunday thing in an hour from now. Just a few words of introduction. Mia joined us in the CBIM program. CBIM is Cloud BIM European Training Network. She joined us in December, history now that we've reached December 2024, when it was at the height of the COVID pandemic. Everyone was working remotely, and Mia joined us to begin with remotely, and then here at Technion, and as an employee of Trimble. Mia did a Bachelor of Engineering in Hydraulic and Power Engineering, Hydropower Engineering at Yangzhou University, finishing in 2016, and then a Master's of Engineering in Water Conservancy and Hydropower Construction and Management at Hohai University in Nanjing. And finally finished an MSc in Applied Computational Science and Engineering at Imperial College. So she came to us with a very rich background and a very vibrant personality, and with a big smile. And I'm happy to say that her smile is as broad today as it was 4 years ago, perhaps broader. So Mia, with that introduction, let's hear about Cloud BIM and how it might be used in the future.
Okay, sure. Let me share the screen. Entire screen, share. And can you see my screen now?
Yeah.
Okay.
We see Greece. Okay, great.
Okay, great. So I will start. Good morning, everyone. My name is Siyu Chen, and I'm an external PhD student at Technion and previous researcher at Trimble. Currently, I'm a software testing engineer at Trimble, and my supervisor is Professor Raphael Sachs, and my research topic is Advancing Interdisciplinary Design Collaboration in the AEC Industry, a study on concurrent engineering and cloud BIM integration. While the title is a bit different from the posters, but the content remains the same. So the seminar is divided into 9 sections: introduction, background, objective research questions, methodology, functional requirements development, experiments, reflection, discussion, and conclusion. Introduction. Interdisciplinary design collaboration is essential in modern building design as it requires various stakeholders from different disciplines to design the different systems in the same building, and each discipline use their own tools. We consider the current IDC workflow as sequential. Typically, the architects complete their design and pass it to the engineers, while the engineers may work in parallel, but there is no or little communication between the discipline. So in the end, the models will be gathered as the IFC files for clash detection, and the clash will be sent back to the corresponding discipline for correction, and the process will repeat until the clash and the design issues are resolved. This workflow leads to 3 key problems. First, late clash detection. It leads to the delivery delay and the increased cost. Second, the lack of early integration of downstream concerns. This limits the insights of the engineers early on. There can be the conflicts at the later phase requiring substantial rework. And third, poor model exchange processes. Since the workflow is file-based, it can introduce the risk of data distortion that require manual check and rework. So let's consider the ideal concurrent workflow by bringing the engineers earlier on the design phase and eventually bring the clash detection earlier on the design phase. So from the picture, you can see that theoretically, it can solve the problem of the late clash detection and lack of early integration of downstream concerns. However, the problem of poor model exchange processes become even more severe as the concurrent workflow requires more frequent updates and the alignment across disciplines. So we need a high level of interoperability and automation to enable this. That's why we introduced this. How can I make it here? Okay, so that's the reason we introduced the C-beam paradigm as the potential technology enabler, which claims to turn the file-based exchange into the object-level exchange by utilizing knowledge graph, which consists of nodes and the edges. So let me give you an example to understand the basic of knowledge graph if you don't know that before. So let's say the node 1 represents the nodes represents the objects in the beam models. The node 1 let's say represents the windows in an architectural model, and then the node 2 represents the corresponding openings on the wall in the structural model, and then edges represents the relationship between the two objects. So the window is inserted into these openings, and the opening hosts the window. So there is this potential scenarios that when the architect decide to remove all of the windows on the wall, then for the structural engineers, there should be an option in the system for him to remove the openings on the wall automatically to keep the design change consistency. So with this graph within the discipline, the graph enables object level and real-time updates. And across the graph, across the discipline, the graph links the model for coordinated cross-discipline changes. And this helps us to solve the third problems potentially can solve the problem. So now we have the ideal processes of the CE, concurrent engineering, and the potential technology of C-beam. What about people? Are people willing to use this? What kind of functionalities they require? Are people ready for the future processes? If not, what can we do to help them to get used to this process? How technology can play a role in this part? To answer all of these questions, we introduced the PPT framework, People Process Technology, which is widely used to enhance the performance by integrating these three elements and perfectly aligning our research on enhancing the IDC performance. So the research focus is to explore the synergy between CE and C-beam and the critical role of people in advancing IDC. Then we move on to the scientific background. I will expand on the state-of-the-art IDC, challenges of the current IDC, and the potential solutions, knowledge gaps. Throughout this section, I will use this PPT framework to guide the analysis. So for the state-of-the-art IDC enablers in AEC industry, the process enabler is the ISO and the Common Data Environment. The ISO is an international standard for managing asset information using BIM. It established a framework for collaborative workflow and the best practices, while the Common Data Environment implements these processes by serving as the platform for managing, sharing, and approving information across the disciplines. In the industry, we currently have many tools for enabling CDEs in the CDEs by incorporating different models from different disciplines, such as Trimble Connect. We gather the model for reviewing and clash detection and assign a task and following the ISO standards. And there are also other similar tools like Trimble Connect. However, the ISO and the Common Data Environment were designed for the sequential workflows. Thus, it still has the problems we mentioned before: late clash detection, lack of early integration of downstream concerns, poor model exchange processes, and what's more, the current CED tools restricted the functionalities that it only limited to the viewing, clash detection, and task assignment, instead of constraining the tools to enable more advanced workflow. So let's explore the potential solutions. For the process enabler, we introduce concurrent engineering, which is a methodology that emphasizes task parallelization, early integration of downstream concerns, and enhanced information exchange. As we mentioned before, it perfectly aligns with the problems of the IDC and solved the previous two problems. of the late clash detection and lack of early integration of downstream concerns. The CE was developed in the late 1980s in the manufacturing industry and was introduced to the AEC industry in later, and the prominent studies in the AEC industry was before 2010, focusing on the theory development like foundational frameworks or the methodologies, and its application in the AEC also includes in the organizational assessment tools, the development of technology tools to optimize the processes, and the educational initiatives to foster collaboration. However, limited research exists on CE in IDC with the current tools, particularly on how these tools and processes can be effectively integrated to address the unique complexities of the IDC in the AEC industry. Therefore, we introduced this C-beam paradigm, which was proposed by the C-beam group at Technion. Yes, it's our team. And the C-beam paradigm envisions the designers from multiple disciplines working in parallel while maintaining consistency and integration at the object level. So in addition to the knowledge graph we introduced before, enabling the object level real-time updates and cross-discipline coordination, it further unleashed the functionality with the AI power by capturing the design intent and ensure cross-discipline consistency automatically. But most importantly, it also integrates the CE principles. That is the reason the C-beam is not only the technology enabler, but the overlap of process and technology enabler. That's the reason we use CE as the conceptual foundation for this research. But again, what about the role of people? In a CE readiness research, it says that the people element of the CE readiness is the most important. And in a human-centric research, it claims that the technology-driven development often overlook the importance of stakeholders' engagement. Therefore, we explored the human-centric research on the IDC, and unfortunately, there is a lack of this kind of research in integrating tools, processes, stakeholder needs, and collaborative behaviors to address the IDC's unique challenges. On the overlapped part of people and technology, the user preference for functional requirements are underexplored. There is some research proposing functions, but it's supporting sequential workflows, not concurrent. And the C-beam proposed initial functionalities, but lacks specificity. And for the overlapped part of people and processes, there is limited research on necessary collaborative behaviors for CE implementation for IDC and minimum exploration of the implementation barriers and strategies to address them. Therefore, to fill the gap, this research aims to advance IDC in AEC industry by integrating CE principles and emerging cloud beam technologies through human-centric research. To do so, we have two objectives. The first one is to elicit essential functions and functional requirements for future paradigm. And the second is to compare C and SE in light of the implementation barriers and the necessary collaborative behaviors. To achieve the first objective, we have three research questions. How can the principles of CE be effectively applied to Cloud Beam for IDC? This already been answered by the C-beam paradigm, so we will not address this problem here. The second is that what are the key problems in IDC with current beam tools? Third one, what function and the functional requirements are essential for future paradigm to support effective IDC? And for the research, the objective 2 is the same. We have three research questions. First, can CE improve in building design in terms of design efficiency, design quality, and technical coordination quality compared to SE? Second, how does CE with Cloud Beam tools impact design processes and collaboration dynamics? Sorry. Third, what insights can be gained to develop cloud BIM technology for collaborative behaviors and see implementation in IDC. To answer all of these questions, we adopted a human-centric design science methodology. For the human-centric approach, we've been emphasizing so far, and it is part of our goal, that to focus on understanding and addressing the needs, preferences, and behaviors of people involved in a system or processes. The methods including survey, interview, and observations. And for the design science methodology, it focuses on creating and evaluating artifacts such as tools, models, or frameworks to solve complex real-world problems by iterating innovative solutions in underexplored areas, which exactly is the reason why we want to use it in here, because the future paradigm is unclear in the interviewees or the participants' mind. So we have to design the artifacts like UI mockups to show them this is your future tool, and then elicit the feedbacks. And also we design the experiment for the future processes and then put the designers into the processes, let them give us the feedback. And this methodology has 6 steps: identify problem, define objects, design development, demonstration and experiment, evaluation and optimization, analysis and learning. And this design science methodology serves the human-centric approach in our context. Now let's see how these methods achieve these objectives. For objective 1, to elicit essential functions and functional requirements, we design the use case scenarios and UI mockups and demonstrate them in the interview to gain the feedbacks. And in addition to interviews, we also conduct survey for evaluation in this part of research. And for the objective 2, we design the experiment tool for the later experiments conduction, and they are for the observations. And then later we also conduct the interview for the reflection on these experiments. Okay, now let's move on to the first research part, the function and functional requirements of cloud BIM systems for IDC. Here is the detailed methodology for this section. So the yellow box are the steps in the design science methodology, and the orange one is the structure for this section. For the research part 1, we have the first round of interview to identify the problems in IDC, and then we conduct survey to evaluate those problems. In the end, we get the key problem of IDC, and based on the knowledge we gain from the research part 1, we design our initial scenarios and the UI mockups and demonstrate them into the second round of interviews and get the initial functional requirements. And based on this round of interview, we also get the feedback to refine the scenario and UI mockup, and we conduct another round of interview for the final functional requirement. And because this part is iterative steps, so I will only show the final scenarios and the functional requirements. Okay, let's get to the first part of this research. We conducted 4 semi-structured in-depth interviews asking for the participants their working experiences, design collaboration challenges, and the corresponding real-world scenarios. And here is the profiles of the interviewees. They gain the working experience in this industry. And to analyze this interviews, we use this thematic analysis. So basically, the transcript of the interviews are the qualitative data. We label them coding them, or actually labeled them, and then later, after iterative comparison, we group them into the themes. So in the end, we identified 15 problems for IDC, and in here, I will not expand because I will cover the details later. And with these 15 problems, we conduct the survey to evaluate them. We received 23 valid respondents, and the profile of the role and experience are also very well distributed. And in the survey, we basically did the risk assessment of the problems. So we asked the respondent to evaluate the likelihood of a problem meaning the frequency of the occurrence of the problem in the project, scaling from very low to very high, and then later we turn that into the number for calculation. And the same, we ask them to evaluate the impact severity, basically the consequence of the problem, and also we have the scale. And in the end, we have this calculation and rated the problems. And the top problems are the inaccurate cost estimates, manual design change tracking, untimely cost estimates, manual design change accommodation or rework. So it aligns the design change relevant problems aligns with these poor model exchange processes. So based on this and the scenario we collected from the designers, we decided to design the use case called interdisciplinary design propagation when adding a staircase. We use this Trimble office model for our use case design, and there are 4 stakeholders working on this use case. So basically, it is the client required to add the staircase in the building in the kitchen area to link the 3rd floor to the 6th floor. And then in the end, we refined 4 scenarios. They are design issue avoidance, clash avoidance, design change management, and error correction. I will only show you one scenario, design issue avoidance, briefly in here. So basically, the architect has to create an opening on the floor to insert the staircase. After she creates this opening, the system pop out a red highlight. So she checked this highlight, and then there is this design issue warning saying that this change will cause a design issue with the structural model. So she just clicked review, and the system will demonstrate the design issue that the opening will cut through 6 hollow core slabs in the structural model, which is not cost efficient. So the architect decided to consult the structural engineer, and the structural engineer suggests her to rotate the opening by 90 degrees so that it will only affect 2 hollow core slabs. And then the architect received this proposal. She felt it is reasonable, and then applied it. So the system will apply it automatically for her. So this is basically what I demonstrate in the next 2 rounds of interviews. So for the second round of interview, 9 one-on-one interviews and 4 focus groups, in total 22 interviewees were involved to elicit initial functional requirements. And in the 3rd round of interview, 9 focus group involving 49 participants were there to refine the functional requirements. And here's again the role of the profiles of the role and the experience are well distributed in both of these 2 round of interviews. And again, we use the same method to categorize the problems, the functions. So, but for the functions, we categorize them into essential and non-essential function. The essential one are the one directly depending on the graph representation data structures we mentioned before, and the non-essential one, they don't directly depend on that. And in the end, we grouped 8 functions, and 5 of them are essential. They are impact analysis, automatic issue detection, integrated platform, automation, tracking, and documentation. And then 3 of them are non-essential. They are notification management, visualization, review, and authorization workflow. And here I will show you some examples of the functional requirements for the function impact analysis, and the details of other functional requirements, please refer to my thesis. So the function impact analysis refers the system can predict the effects of the design changes on various aspects on demand. For example, it requires the functions to have on-demand cost impact analysis of the design changes and the timeline impact analysis, the building code compliance check of the design changes, and the clash detection of the design changes, and the on-demand potential design issue prediction, and the solution recommendations after design changes, and etc. So far, we've also answered the third research question, and I will summarize it later in the discussion section. And for now, the first part of my research has been completed. Let's move on to the second part, the comparative experiments on CE and SE. So this is the detailed methodology, and the yellow part is again the steps in the design science methodology, and the orange part is the section structure. For the first part, we design and refine the experiment setup. So we design the initial setup and test it in the experiment 1 to see if the participants are able to complete or nearly complete the task. And then later we conduct the interview with the participants to refine the experiment. And we test it again in the experiment 2, and this time it was successful. So we conducted additional 4 experiments with the same settings. And in the end, we conduct the interviews with all of the designers in the experiments. And for the research part 3, we will cover that briefly in the section 7. And here we will only focus on the research part 1 and 2. And also because the research part 1 is the iterative process, so we will only show the end result of experiment setup. For each team of the experiment, we have 5 participants. Project manager, BIM manager remained consistent for all of the experiments. The architect, structural engineer, and the MEP engineer, they were different for each team. And for each team, we provided them the same schematic architecture model as the beginning point, intentionally incorporating design issues. And the aim for the participants are to solve the design issue, develop, coordinate, and complete the design. And for the procedure, for both of the CE and SE, the online meeting or the charade, which is the blue box, is the same. It was held weekly for planning, coordination, and clash resolution. But for the offline design session, it's different for them. So for the CE offline session, all 3 designers required to work in parallel for 2 to 3 hours per week for 4 weeks. And for the SE scenario, the designers are required to work sequentially and independently for 6 to 9 hours for 1 week to complete all the design tasks. So as you can see, the architect will finish all her design task in the week 1, and then we will save the last session for them to deal with the design issue and clash detection. So in total, we conducted 6 experiments, 4 CE experiments and 2 SE. And for the comparison analysis, we will only use experiment 2 through 6 because the experiment 1 had different setup. Oh, and also the designers, they use their own familiar tools for BIM design, and we use email, G Drive, Google Meet, and the chat for the communication tools. For the common data environment, we use Trimble Connect. And here is the design outcome of all of the groups and the disciplines. And let's take a closer look at each discipline. That the architecture solution, we evaluate the design quality by the functions and the furnitures, etc. And as you can see, the architectural solutions they are quite different. And for the structure solutions, we evaluate the integrity, file safety, constructability, and etc. And again, it's also very different solutions, and also the structures, they are at a quite good completion level. And for the MEP solutions, we evaluate the main root terminal and air handling equipment, etc. And notably, you can see that 2 experiments in the CE setting, they have this low design progress. It might be because there is some barriers in the concurrent workflow. For example, the resistance to working on the assumption due to the the habit in the current sequential workflow, or because of the delay in receiving architectural structural design. And also it can be because the unresolved upstream issues causing waiting time. To further analyze the result, we group the data into 5 themes: design efficiency, measuring the project time distribution; design quality, assess the progress and the functionalities of the design; team interaction, analyze the communication and collaboration through questions and solutions, the numbers that's in this themes; and the issue clash identification and the resolution, they track the detection and resolution of non-tool detected or tool detected design challenges. So these two themes represent the technical coordination quality. And with this information, you can understand the design efficiency, design quality, and the technical coordination quality in the research question 1. Here are some example metrics in the theme team interaction. For the simple metrics, this is some metrics you can count directly. For example, the total turns, meaning the total speaking turns taken by each group, reflecting the level of engagement in the discussions. And the interaction variation, it is the metric that requires calculation. This measures the variability in speaking turns. The lower values indicate more balanced participant engagement rather than one person speaking and dominating, other person remain passive. So here is the result for the theme design efficiency. If you look at the online session time for discussion, that the CE groups spend much more time than the SE groups per session. And here I would like to point out that the group 2 is an outlier, and I will expand more on the next slides, but it is worthwhile to notice that in this slides that the group 2 complete the projects in 3 sessions instead of typical 4. And then if you look at the time on management for the online discussion, that the CE group spent much less time than the SE group. And if you look at the time on the issue discussion, that the CE group spent much more time than the SE group, then we can say that the CE group spent more time on issue resolution than on management activities. And here is the result for the design quality. So we have the evaluators to evaluate this according to our standards. And if you look at the project design quality in the end, there is no too much difference between these two groups. But if you look at the group 2, it stands out with significantly higher quality, which indicates that certain collaborative behaviors can be a strong factor, that the approach alone may not be a decisive factor for this design quality. But we have to acknowledge the limitation in here, since each project took us around 2 months to complete, resulting in the limited number of these experiments. It might restrict the generalizability of the findings. However, hopefully it still can provide some helpful insights. And if we look at here, the issue identification and resolution and the clash identification and resolution, if you look at the number of issues identified in early weeks, in week 1 and 2, it is obvious that the C enables early issue and clash identification, since the SE has 0 identified in the previous 2 weeks. And also, if you look at the total number of issue identified, the C enables more issue and clashes to be identified. And if you look at the discussion time per issue, the CE groups are more efficient in resolving individual issue and clashes, that they spend much less time per issue and clash. Here is the result for the team interaction, that if you look at the number of questions asked per session, and the number of solutions per session, number of the speaking turns, you can find that the CE foster greater team interaction compared to SE. And this also applied to the interaction variation because the lower values indicate more balanced participant engagement, and the C groups get the much lower values. Again, if you look at the group 2, this group has even higher number of question and solution and the speaking turns and even lower interaction variations, which might indicate that the effectiveness of CE can be strongly influenced by proactive problem identification, collaborative brainstorm, balanced participation, and dynamic turn-taking in team interactions. Okay, let's move on to the reflections on the experiments. So we conducted 18 interviews with all of the designers in the experiments, and here I will just show you some examples of their reflections on concurrent workflow due to the time limitation. So the designers point out that while CE can significantly speed up the processes ideally, its inherent complexities demand better management and more interactive communication. And the designers also emphasize the importance of detecting clashes before the updates because this would reduce the workload for the BIM managers and streamline the workflows. And last, tracking when dependent tasks are completed is crucial for the parallel work, and the timely notification can prevent delays and streamline the workflow. In general, the participants' insights largely confirm the relevance of functional requirements and experiments findings. And the experimenter's reflection is my reflection is that to facilitate C implementation in IDC, we should prepare the role beyond just technical specialists. We have to prepare the role like communicators, integrators, and decision makers by focusing on bridging gaps, aligning perspectives, and driving decisions. And for the education and training, it is important to simulate real-world scenarios to teach teamwork for practical challenges, helping the individuals identify the strengths within the team dynamics early in their college life. Okay, let's move on to the discussion to address the questions. For the objective one, second research question, what are the key problems? We identified 15 problems and rated them, and the key problems lies in the cost and design change relevant issues, which is aligned with the poor model exchange processes that we identified earlier. However, there is no clear mention about this late clash detection and lack of early integration of downstream concerns, which might be because it is the workflow relevant problems that people get used to the current problems. So current sequential workflows, they don't feel it is necessary and the late clash detection has any problem because it's just normal. However, we can see that the delayed delivery of design models and lack of a communication can reflect the problems in this too. And for the research question 3, what are the functions and the functional requirements are essential for the future paradigm? We identified 5 essential functions, 3 non-essential functions, and we also rated the functions by counting the times that interviewees propose the functional requirements, that we can see the impact analysis is the functions that the designers required most in this era. And compared with previous research, this research expands the CBIM's initial functionalities by providing detailed functions and functional requirements. And the most important function shifts from the customized interface to the on-demand impact analysis, which is aligns with the modern workflow needs. And for the objective 2, the research question 1, can CE improve building design in terms of design efficiency? Yes, CE groups allocated more time to issue resolution and resolve the issues faster, streamline the processes. And in terms of design quality, CE has the potential to improve quality but does not guarantee it, since the experiment 2 achieved significant high outcome. It shows the potential. However, the results from the experiment 3 and 4 shows that the CE's effectiveness heavily depends on the collaborative behaviors. And in terms of the technical coordination quality, CE enables earlier issues and clash detection and resolve them more efficiently. And yes, so it can enhance the team alignment and coordination. The second research question: how does CE with Cloud BIM tools impact design processes and collaboration dynamics? In terms of design processes, CE promotes early issue and clash identification, enabling efficient issue and clash resolution and smoother workflows despite the potential increased workload of the more clash and issues. And in terms of the collaboration dynamics, the CE with current tools can foster better team interaction, supporting real-time, ideal sharing, and decision-making. Third, what insights can be gained to develop cloud BIM technology for collaborative behaviors and CE implementation in IDC? For helping the CE, the tools should integrate the chat functions and shared workspace to sustain the interaction and coordination according to the finding 7. And for the collaborative behaviors, the tools should support proactive problem identification, brainstorming, execution through the features such as the AI-driven early issue or clash detection, AI-generated solution proposals, dynamic issue tracking, and the documentation and action assistant systems. And compared with the previous research in terms of design quality, efficiency, and coordination of CE, this research extends the CE's application in IDC by highlighting the collaborative behavior as critical for design quality, aligning with the statement of the people elements of the CE readiness is the most important one. And this research also confirms the CE's coordination benefits, but notes the increased clash management complexity, which requires further technological and behavioral support. And in terms of collaborative dynamics and supporting technologies, this research reinforced the previous work on the importance of proactive teamwork, emphasizing the behaviors like proactive problem identification and creative brainstorming. And it also provides the actionable insights for the development of future tools, focusing on how these technologies can facilitate and enhance these essential collaborative behaviors. Limitations. So the general limitation of this methodology is that the human-centric research is always a bit subjective, that might get affected by the researcher's personal perspective and value. It might introduce the bias in the result findings. And the second, the sample size of the experiment is quite small, that might restrict the generalizability of the findings. And the controlled experiment settings cannot fully capture the complexity of the reality. And conclusion. This study aimed to advance IDC in the AEC industry by exploring the integration of CE principles and cloud BIM technology through human-centric research. And this research divided into two parts: the functional requirements development. In this part, we identified the problems, essential functions, and functional requirements, and designed the UI mockups for the future paradigm. And in the second research part, the experiment comparison, we designed the experiment tool and conducted 5 experiments. And I will skip the key findings here. And for the contribution to knowledge, this research expands the understanding of CE's role in IDC by highlighting its impact on design efficiency, etc. And the research identifies the key barriers to CE implementation, primarily the inefficient collaborative behaviors. For the practical contribution, this research defined essential function and functional requirements for future paradigm, and it also developed reproducible experiment tools and UI/UX mockups offering reusable assets for the future research in this area. And for the methodological contribution, the research validated the integration of human-centric approach and design science methodology, providing a framework for future research in this area. Future direction. So this research has already identified the many barriers and factors affecting the CE implementation. The future experiments can focus on the specific variables identified in this research to further push the boundary of advancing IDC. And it is also necessary to explore the human factors, because if we want to implement the CE processes, it's important to get people ready in the education and training. Although we touch a bit about this aspect, but it still need to do the research more on the collaborative behaviors and the course design in the future. And it is important to use the advanced cloud BIM tools in the future research to make sure the future research align with the industry standards and the technological capabilities that's emerging, and ensure the research is relevant and effective all the time. So this topic is at the forefront of both academia and industry, which makes this research central to advancing interdisciplinary design collaboration. And by integrating these three elements, the future research can align with the broader goal of CBIM paradigm, ensuring the practical and impactful contribution to the AEC industry. Thank you. That's all for my presentation.
All right, so I suggest we show our applause both digitally and manually, literally. Thank you very much, Mia. That was right on time, perfectly on time. So I guess let's open up the floor for some questions or discussion or comments. You're all welcome to join in.
Yes, please. Connor? Oh.
I'd be happy to kick off if you don't mind.
Sure, please go ahead.
So really, congratulations, well done. That was a lot of, firstly, a lot of people to pull together. I think it's really remarkable, and no better person to pull so many people together. Like, you had to manage a lot of relationships in conducting all of that qualitative work. So I think that's really impressive. The second thing is just a question. I think your work relates quite a lot to efforts by Building Smart International, obviously. And I was wondering, had you thought about perhaps contributing on the BIM collaboration format, the BCF work within BSI? Have you thought about maybe getting involved with that community? I think they'd be really interested in your work.
Oh, yeah, maybe in the future it's possible. Yeah, because currently Trimble also, the Trimble Connect is also trying to use the BCF right now instead of the to-do list we used before. So I think it might be possible, and we are also the part of the community, the Building Smart community. So that's possible.
Excellent. Can I have a second question?
Okay, sure.
You're on a roll.
Yeah, so you did this work from within somewhat one of the large tech vendors, one of the proprietary tech vendors. Do you get a sense that incorporating things like the topics you were talking about, graph technology, do you get a sense that the big vendors are interested in that, or is it a priority for them?
I think what they want to achieve is the same, that to update this object level. So for this kind of those kind of math, I've also investigated a little bit. It enables people to upload the like a single object, but I'm not quite sure about the relationship between the objects. So I think it might be something in the future, but currently it's not in short term, I think.
Okay, thanks, Emil. I'll pass on.
Yeah, I'll
Okay.
just comment on that. And I think that the challenge for many of the tech companies, especially the 4 or 5 big ones, is that they have a very big legacy investment in software which works with files. And their internal schema are arranged in such a way that they can write to files and read from files. So their ability to switch to an entirely different paradigm where they have a graph database is quite limited. Not because they don't know how to do it technologically, but because the amount of effort required to flip their current products would be very big. So I expect that unless they're forced to do it by competition and so on, then they'll remain with where they are because the profit margins are too high or too comfortable, let's say, for the technology that already exists. It doesn't need any more investment. Yeah, other questions, comments?
I mean, I have more, but I'll
Let's see. Any others who are taking part? No, so Connor, go ahead.
So I was saying you pulled together loads of people. I mean, at one point I saw 49 interviews. There were loads of focus groups. Very impressive. You must have made loads of relationships over the last 4 years, I'm sure. What I was wondering was you described a really impressive experiment in the second part of the research. So the part where you were talking about running over a month online and offline a project. So
Yeah.
that was a kind of a mock-up project, like it was a kind of a fake project in a way to test a hypothesis, right?
Yes.
So how, I mean, that's pretty impressive to convince a load of different designers to commit to that for academic purposes. How did you manage to do that?
I think first of all, I put a lot of effort to spread the news. Oh yeah, I remember. I joined the I joined the class in the a course in Aalto University, and then I find half of the designers from that course because I spent like 3 months with them for the courses, and then I just know many people in there. They have the working experience that here in Finland. So most of them, they are from that group, from the course. And another part that I did a lot of news spreading and reach out people on LinkedIn and just type structure engineer and then send them the messages. Okay, many people, most of the people don't give me a shit, but but eventually I got enough people. And also, of course, you have to provide some incentives. Yes, so that's how.
What was the incentive that you used?
So for first of all is the 200 euros gift card, and then because you required them to contribute nearly like 20 hours on this project, and then the second is a certificate for this project. Yeah.
That's excellent. Well done. Congratulations. That was a huge amount of relationships to manage. And the people, as you identified, is the difficult part in all of this, not the technology. So well done.
Thank you.
And I really appreciate the question. And this has been through the period of the research and is really challenging to create experiments that are that can be recorded and can be analyzed in detail, and that every statement or every use of language during the experiments can be recorded and analyzed in a very thorough and rigorous way. And I think that's what Mia has achieved, and which gives this experiment its huge value. And obviously, mobilizing all those people was an enormous effort. not just mobilizing them, but keeping them engaged. There were many who became engaged and then dropped out, which then invalidates the experiment. I think we're only seeing the complete ones. There were others that were abandoned along the way or had to be abandoned. I think, Mia, it's true to say also that during the year or the many months, I don't recall if it kept a whole year, while you were here at Technion, you also took part in the advanced BIM class here, which I think gave a very strong perspective on how interdisciplinary groups work. And then taking a similar course in Aalto afterwards, you already knew the material, but it afforded an opportunity to engage the people.
Yeah, and I think the course in Technion at Technion is also very important because I invited them for my first part of research for the focus group and the interview. So many of them, they also provide me very insightful opinions. Yes.
I think it's one of your strong skills, the ability to engage and work with people, which made this research possible at all. Without that skill and talent, might not have been possible.
Thank you.
Other questions? I see Duigu, I see Tanya, I see others, many others. Any other questions before we close off?
Just one, if I can. In one of the tables, and I'm sorry, I don't remember the number of the slide, but you showed there's a difference between management efforts and clash detection efforts. So what is the difference between the two? What do you call management? Yeah, it was somewhere here.
Yeah. So the management activities means that we only report the progress and then describe what we have done and what we should do next. But the issue discussions, meaning that they start to discuss, okay, here there might be a problem, what do I need and what can you do? So they are trying to discuss and solve the issue and push forward the progress of this design.
Okay. Okay, thanks.
Thank you. Hey.
And we have sharpened us the difference between issue discussion and clash discussion. Okay,
so issue discussion is the non-tool detected problems that it's not later we use Trimble Connect to identify what is the physical clashes, but before we identify the clashes, people see, okay, here there might be some problems. I need to clarify some information. We need to get some information and then to move the progress forward rather than we get the result and fix it.
All right. Tanya, did that answer the question?
Yeah, it did. Thanks.
Okay, fantastic. Okay, I think we're exactly on 10:30. So unless somebody has a burning question, I don't see any, then we're going to say thank you very much, Mia. We'll give you some applause to congratulate you again on a great piece of work.
Well done, Mia.
Thank you.
And we wish you luck on completing the thesis and submitting, and we'll meet sometime in January, I hope, February for the exam. Again, thank you very much. It's interesting. I will just add this for the sake of those who are in CBIM. We received on Friday the final confirmation from the project officer that everything is complete and done, and they're very satisfied.